Welcome to Lesson 11b, Particle Plumes and Puffs. We're going to analyze Gaussian particle plumes where we incorporate particle settling into the plume. We'll do the same with puffs. So for a quick review, let's remember our Gaussian plume. We always did this for gaseous air pollutants previously. And I note that particles are always absorbed by the ground. So if you have some particle coming along and it hits the ground, it's going to be absorbed into that ground. Later on, there could be some high winds where this particle can get resuspended and may move around a while, but eventually it's going to fall back down. We're not worried about any of that. We're just going to assume that as soon as the particle hits the ground, it is absorbed. Well, what that means is that now we do not need to calculate the reflecting ground case. We'll look at absorbing ground only. And this applies both to the plumes and to the puffs. So that makes our life a little easier. Let's review our workhorse equation we had previously for a buoyant Gaussian plume with an absorbing ground. This was our equation for mass concentration at any x, y, and z location. So this is all review. You know how to calculate these sigmas based on the atmospheric conditions. We had to pick a class, you find those sigmas, and then you plug into this equation for a given x, y, and z. So at any x, y, and z location, we already know how to do this. And here's the sketch of that plume. Remember, we used an effective height h that was equal to the stack height hs plus some delta h due to buoyancy. So we put our source there and the plume spreads out and eventually hits the ground here, etc. And we know that at any x location, we have a Gaussian when we plot Cj versus the vertical elevation. So that's all review. Now, how do we modify this for a particle plume under the same conditions? And of course, we have an absorbing ground. We'll always have an absorbing ground when we deal with particles. Well, I copied and pasted this plume from above, except I colored it gray. And what I'm showing is that this whole particle plume tends to move down. Notice that the center line of this gaseous plume is flat. It stays at a constant elevation, and that's what we call h. And these particles all move at some wind speed u on average. Well, for particles, I just took this plume and tilted it down because what happens is you have the same u, but you also have a vt, terminal settling speed of the particle, and then these have to be added vectorially, so the overall little v of the particle vector is down and to the right. We did the same thing with uniform wind. Now we're inside a plume. The key is to superpose vt onto our existing plume. And what that does is just tilt the whole thing downward. Notice this black center line for the particle plume is tilting downward. My particle plume is gray to indicate that it's particles. As far as the spreading in this turbulent plume here, depending on the atmospheric conditions, that's all taken into account by the sigmas. So the spreading will be the same. It's just that over the whole thing, we have some VT added because the particles are settling. At some cross-section through this plume, we still have a Gaussian, but it's kind of tilted a little bit down like I draw there. But normally this angle is really small because as you've calculated, VT is typically really small compared to capital U. Note also that turbulence is already taken into account by our dispersion coefficients, sigma y and sigma z. Those are related to how stable the atmosphere is and how fast it spreads. And like we did last lesson, we don't really care about all these individual eddies and stuff with turbulence. We only care about the average U and the average VT. So we're doing this vector diagram just like we did for a particle settling in a wind. Now we have a wind, but we happen to also be in a Gaussian plume. So we ask how to incorporate VT into our Gaussian plume. Well, go way back when we introduced Gaussian plumes, and first we had a plume all by itself kind of up in the sky somewhere, and we accounted for the height of the plume by replacing z by z minus h. That accounted for plume elevation, so that z equals 0 at the ground. Well, we want to do the same thing here. This was kind of a trick. We'll trick it again, where we let h, instead of being a constant, we set h equal h of x. If you look at the plume, the center line is just linearly falling at this angle. So instead of h being a constant as it is here, we can set our h to be h naught at the beginning, but h will be decreasing as we keep going downstream. Eventually that center line is going to hit the ground actually. So you can see that h is decreasing linearly with x. And that's a little trick, just like we did before to change to z minus h. Now let's change to z minus h, where h is now a function of x. Well, what is this function? It's h naught, the value at x equals 0, minus vt times the time. Speed times time is distance. So let me label these things. H naught equal h at x equals 0. And at some x, the particle has fallen this distance, and the time is just x over u, since the particle is moving at a constant speed u in the x direction. So let's substitute this into here, and we get our expression for h of x. Namely, h of x is h naught minus vtx over u. So plug this into our Gaussian equation. Everywhere we have an h, we're going to replace it with this expression for h of x. So go back to our original equation where we have an h. Just replace that h with this equation h of x. It's just a nice little trick. So that's all I did. The final equation then is this equation for a particle plume, and it's always going to have an absorbing ground. I'll stop even saying that. Anytime you have a particle plume, you have to have an absorbing ground. So all we did was change that h to this expression for our effective h. And that's all there is to it. This equation is on the equation sheet, by the way. Now, very quickly, we can do exactly the same thing with the particle puff. So I go back to the Gaussian puff, again with an absorbing ground. We had this equation. Again, we replace our h with exactly the same effective h that varies with x to get our final equation for a Gaussian particle puff. And that's all there is to that. This equation is also on the equation sheet. Well, since you've already done Gaussian plumes with gases and you've done Gaussian puffs with gases, you can easily do now Gaussian plumes and puffs with particles. What you need to do, though, is find this VT. So we're combining stuff that we've been learning recently about particle settling with the stuff we've learned a couple weeks ago with Gaussian plumes. Here's an example. I picked a particle plume instead of a puff. I could just as easily have picked a puff. So here's my particle plume that's settling to the ground. If you look back, everything's the same as our standard example problem that I gave many times. This goes all the way back to lesson 6D, where we had a simple gaseous plume with an absorbing ground. So we really don't care what happens under the ground. Now all I did was tilt the plume, and we're going to use this little trick with the H. We have some stack height, we have a buoyancy, additional elevation, just like we had before. This we're now going to call H naught, and at any location downstream, call this X1. This would be H at X1, and you can see that H keeps decaying as we keep going downstream, and it's just linear. So let's look at the given information. Here we're at SATP. I can give you different temperatures and pressures for homework and quizzes, etc. We have a stack height, so this would be our HS. And then we have a buoyant plume, so the delta H is 20 meters. So our H naught in this case is 100 meters. These are the same parameters that we had with the previous problem in lesson 6D. Same average wind speed, same source strength, but now we have particles. So I picked a particle diameter, dP is 10 microns. We're going to use the same conditions we had back in that old example problem, which was an overcast morning. And I want to estimate the maximum mass concentration of the air pollutant at ground level. So maximum, that means y equals 0. You're directly downwind. At ground level means z equals 0. And we give some x location, same one we gave in the previous lesson. I do want to mention that these equations, either for plumes or for puffs, are valid for any x, y, and z. I just happen to be looking in this example at the simple case where we're at the ground, so z is 0, and we're on the center line of the plume, so y is 0. By the way, if you look back at that lesson 6D, our answer was 74.7 milligram per meter cubed at this x location on the center line and at ground level. I'm going to compare that to what we have with the particles. So our solution. First, we calculate the air properties. Normally, we use the ideal gas equation, Sutherland equation, the mean free path equation. Here it's at SATP, so I can just look these up on my equation sheet, but you should have these programmed into your computer already. I get 1.184 for the density, 1.849 times 10 to the minus 5 kilogram per meter per second for mu, and lambda is 0.06704 microns. Next, we need to calculate the terminal settling speed of these particles, and you should have that programmed in already. So for a given particle size and density, and for these air properties, you need to iterate along with the Cunningham correction factor, the Morrison equation, and you know how to do that. You see why I told you to program these up in software, so this should be just trivial for you now. To calculate, make sure you get my answers like always, 0.02621, I'll give 4 digits here, meters per second. Is what you should get for VT for these particles. Next, you calculate the dispersion coefficients for this atmosphere using those tables, the Martin model. This turns out to be class D, from which at this given x we can calculate sigma y, 278.973 meters, and sigma z, 87.5085 meters. By the way, those are the same as previous example problem of 6D, because I'm using all the same parameters except I added the particles. And then we apply our Gaussian plume equation that we had modified for the settling particles. The only difference is this part here. First, all the terms before the exponential term, all these guys, and I put in 1 unit conversion factor. This will come out to milligram per meter cubed, which is what I want. And then I have the exponential term. For our particular case, y is 0, so that whole thing goes away. Z is 0. The negative sign doesn't matter when we square. So all we have is this h term in the sigma z squared. So I have my negative half here, and then everything on top in brackets, h naught, and then here's my VT. My x, notice I changed to meters so I don't screw up my units, divided by u. And then there's a sigma z in the denominator, so I put all that in brackets, plug in my sigma z, close my parenthesis, square it, close my squiggly brackets, and I get to 3 digits 99.8 milligram per meter cubed. As I always say, make sure you get this answer, and then you should have no trouble with the homework or quizzes when we do such things. By the way, this is very powerful. We can now predict where particle plumes are going and how much concentration there is at any location downwind of the plume. And it doesn't take much to change your Excel or MATLAB or whatever program you have. Just by everywhere you have an H, you plug in this expression for H of X, which is literally all I did in my Excel program to get this answer. Thanks, Professor. Changing from gases to particles ain't as hard as I thought it would be. That's right, Dud, especially if you have all these plume and puff equations already in your software. And I did that. Then you should be all set to go, Dud. Just a few comments. Let's compare with what we had for the gaseous case. Notice it was 74.7. Now we have 99.8 milligram per meter cubed. So let me make some comments. The first one, as I just said, here Cj of the particle is greater than Cj of the gas, the gaseous air pollutant, for the same conditions. And we should expect that. For the gaseous plume, we have something like that we've drawn many times, where we have our source above the stack. For the particle plume, we have the same spread, it's just tilted because of VT. So the particle plume hits the ground at a closer X location than the gaseous plume does. The particle plume hits here, and the gaseous plume doesn't hit till there. So our X location is somewhere here probably, where this location is closer to the center line of the particulate plume than it is to the horizontal center line of the gaseous plume. So we expect that concentration to be higher. So that makes sense. But I want to warn you that this is not always the case. It depends on the particle size. For heavy or large particles, the top of this particulate plume, notice I drew that slightly upward here, but if you have really heavy particles that are falling fast, the top of the particulate plume can actually slope downward. This also greatly depends on the atmospheric stability class. But let me try to sketch that case, and I'll look from further away. There's my ground, there's my stack, here's my source, here's the gaseous plume, which always has a horizontal center line. But if these are very heavy particles, I tilt this at a fairly large angle. Just take this red triangle and rotate it. And if the particles are heavy enough, what happens is this center line, which by the way is always U and VT, add up vectorially to our particle velocity V. Well, you can see you'd have a higher concentration in this region because the particle plume has hit the ground first, just like we talked about up here. But the top of this particle plume actually hits the ground, and nothing under the ground matters. It's just absorbing. So eventually, this particle plume gets completely absorbed by the ground. So if you're back here, you never even breathe any of those particles, but you do breathe the gases that come out of that plume. So Cj gas is actually greater than Cj particle here, which is the opposite of this case. Typically, that doesn't happen till very far downwind, and it has to be very heavy and or large particles such that the top of the particle plume actually is tilted downward. But this is all very fascinating, I think. You're able to predict all kinds of stuff with both particles and gases for these plumes. Pretty much everything we've said about plumes also applies to puffs, except you're dealing with dose instead of concentration. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.